Welcome to Talking Science, where we dive into science and space. Dr. Lily Sutton is here to discuss boson clouds. Lily, thanks for your time.
Thank you for having me here.
This is Trek Zone's Talkin' Science.
Well, don't forget Trek Zone membership available via the join button under each video on YouTube or via the trek.zone/support. Plus, Trek Zone's on Twitter, Facebook, Instagram, and your favourite podcast feed. Find us, like, follow, and subscribe. Lily, tell us a little bit more about boson clouds and why we're so curious to find them.
Yeah, okay. This is a very interesting study, actually. As many of you might know that we have been looking for gravitational waves from the collisions of black hole, neutron star binaries. But actually, these are not the only types of gravitational waves we are looking for. There are other types of gravitational waves, and they are all very interesting. And the boson clouds are potentially one out of the many potential sources out there. These clouds are made up of ultralight boson particles if they exist. So these particles have not yet been detected. They are so far being predicted by series. They are ultralight. I'm not sure, it's really hard to imagine, they have the mass around 10 to the minus 28 kilogram, something like that. So they barely interact with matter, and they also could potentially be an important component of dark matter. So if we can observe these particles, that will give us invaluable information and significantly improve our knowledge and understanding of particle physics, dark matter, and cosmology. So they are really interesting things to study through the universe and using gravitational waves, and that's why we are looking for them.
Awesome. Well, as I understand it, it's almost impossible to see them from Earth. So how are gravitational waves helping us to look for them?
It's very difficult to detect these particles on Earth, even if they exist around us. So as I mentioned, they have extremely small mass and they barely interact with normal matter. So it's almost impossible to use particle experiments like those particle accelerators and colliders, because those experiments basically rely on the extremely weak interaction between these particles and normal matter. However, what if they don't react to normal matter at all? But gravity is kind of a universal character, and we kind of can take advantage of gravity. So they have extremely small mass if they exist. They will feel the very strong gravity field near the black hole. So a huge number of such particles might accumulate around the black hole and then form such a cloud. And this kind of cloud can extract rotational energy from the black hole, so they kind of grow. And even in some a kind of optimal scenario, they can take up to around 10% of the black hole mass. So they are really something quite significant. And then they start to emit gravitational waves and can live for a very long lifetime. And that could be potentially be observed on Earth with our gravitational wave detectors like LIGO, Virgo, Quagga. So that's how we take advantage of gravity and the feature, the signature from gravitational waves and try to probe these kind of particles.
Well, gravitational waves are a relatively new area of research, as you say, with LIGO and Virgo detectors spanning vast distances in different parts here on Earth. So I'm guessing this is all a little bit of trial and error at this stage, but obviously with the more gravitational waves we detect, the greater our chances of understanding the results are.
Yeah, that's correct. So at the moment, we actually haven't found any signals from these predicted phenomenon. If they exist, they might emit such signals, but we don't see any. But that doesn't really mean they don't exist. So we obviously have better chance when we have better detectors in the future. So as you know, the LIGO Virgo Kagra detectors, the current generation detectors are still being upgraded, and we aim to have better sensitivity for the next observing run. But on the other hand, we are also planning and designing the next generation detectors. They would be much longer and better and more sensitive. So especially with those next generation detectors, we can really reach much deeper in the universe for this kind of boson cloud, like reach billions of years away. And there will be obviously more chance to see a signal if they exist.
Well, we do know a couple of key facts about boson particles and boson clouds. It's highly unlikely that they're in the Milky Way because younger than less than 1,000 years old, they're not going to be around here. And up to 10 million years old, they aren't likely to be within 3,200 light years of Earth. How did the research lead you to those conclusions?
Yeah, so first of all, I want to clarify that these conclusions are based on a particular type of boson clouds, and these are emitting signals within the sensitive band of our detector. So obviously for other types of boson clouds, for example, they produce signal out of the band of our detector, or they live for a very short amount of time, then with the current detectors and techniques, we won't be able to study them. So we cannot make a conclusion on those clouds. But for these types of clouds we study at the moment, these conclusions are based on the age of the cloud. So it's actually pretty straightforward to understand. So if you have some cloud, they are pretty young, and they would produce stronger signals, while if as time goes, they keep emitting gravitational waves, and gravitational waves carry away energy. So they lose their mass and energy, and the cloud shrinks. So, so for stronger signals, like from those younger clouds, because we don't see anything like in our study at the moment, we actually can conclude that they are not likely to exist in the Milky Way because we can actually reach beyond the Milky Way. But if you can imagine, if we have some very old cloud in the Milky Way, but they are emitting very weak signals, however, we cannot really reach very far distance, so we cannot say whether they exist in the Milky Way or not. We can only conclude that they are not likely to exist within a kind of a shorter distance from us. That's the key point.
I understand now. Well, what's next for the research, Lily?
Obviously, gravitational wave science is a very exciting field at the moment, and I feel so lucky and excited to work in this area. For my personal research interest, first of all, the boson cloud, the hunting for boson cloud is still one of my research interests, and I will certainly continue working on that. Meantime, I'm also interested in studying neutron star physics using gravitational waves. Neutron stars are those extremely dense objects in the universe, and we want to study how matter would behave under those extreme conditions. And gravitational waves will help us to understand that. That's also one aspect I'm really interested in. And also, I'm interested in carrying out tests for Einstein's general theory of relativity using gravitational waves and see if there's any deviation between the theory and reality. So with more detections in the future and better detectors, I believe it's a very exciting future in front of us. So I'll be really excited to see those new discoveries.
Awesome. Well, Dr. Sun, thanks for beaming in for this edition of Talking Science. Good luck with your future research.
Thank you so much.